Hello, this is Mr. P, and today we're going to be learning about quadratic functions. Quadratic functions have equations that are second-degree polynomials, so the general form can be written as f of x equals ax squared plus bx plus c, where x is the variable, and then a, b, and c are just numbers. Now, for our purposes, we're going to be working with mostly integer values for a, b, and c, but the analysis we're going to see here does apply to rational numbers, irrational numbers, and even complex numbers for a, b, and c. But mostly we'll be working with integers. All right, the graphs of these equations are going to be parabolas. So if a is positive, then we're going to have a parabola that opens upward, sort of like this. And if a itself is negative, a being the leading coefficient, if that is negative, then the parabola is going to open downward like this. So we'll have one of those two situations. It's not going to open up to the side, left or right, because then we wouldn't actually have a function because it would fail the vertical line test. So in order for this to be a function, the parabola is either going to open up or it's going to open down. Now, if it opens upward, then we can see that as far as relative extrema are concerned, there is a minimum value at the vertex, and there is no maximum value, because it will increase without bound. Likewise, the one that opens down will have a maximum value at the vertex, and then the function will decrease without bound, so it won't have any minimum. So when finding the extremes, either a maximum or a minimum, all we have to do is find the vertex. So there is a nice little shortcut formula for finding the x value of the vertex, and that can be shown here. That is simply x equals negative b over 2a. And the a and the b refer to these two coefficients, the coefficient of the quadratic term and the coefficient of the linear term. Now notice how if a is positive, a being greater than 0 means it's positive, so we're looking at this situation. That means we'll have a minimum at the vertex. And if a is negative, which would be this situation visually, then our vertex is going to be a maximum value. But for each case, notice how the equation is the same to find the x value of the vertex. And once you do know the x value of the vertex, you can of course substitute that into the original function to find the y value of the vertex. That would be one way of finding the vertex. Another way would be to take the equation and complete the square so that we rewrite it in what's called the standard form. And this is the standard form of a quadratic, is f of x equals a times the quantity x minus h squared plus k. When it's in this form, and of course our a cannot equal 0, otherwise we wouldn't have a quadratic, but when it's in this form, it's very easy to find the vertex because it's simply the point h comma k, where k is just whatever this number is on the outside, and then h is the one that you would get when it fits the model x minus h. Now this one can be a little confusing because if we use a numerical example, let's say we have x plus 3 inside our parentheses for some model, then h is not really positive 3, h would be negative 3 in that example, because x plus 3 would be considered x minus a negative 3. So that value of h would actually be negative 3. This can get a little bit confusing, especially when this is the first time you've dealt with the standard form. That's why I believe there's a much better way to understand this, a much better way to think about this. And that is asking ourselves the same question we've been asking in many other cases, and that would be, what is the value of x that causes the parenthesis to be 0? That will be the new x value of your vertex. So in other words here, if x equals h, then that parenthesis is 0. Therefore, h is the x value of the vertex. And we'll see that in our example, and hopefully be a little clearer with actual numbers. Also notice how it does say that if a is greater than 0, the parabola opens upward, and if a is less than 0, the parabola is going to open downward, just like we saw earlier. Alright, so let's jump in with an example. Here we're going to identify the vertex of a quadratic function, and we're going to graph it. They say describe the graph, but we're just going to go ahead and graph it. So we're going to graph this, and we're going to identify the vertex. Two different things they want us to do. And it's actually easiest to find the vertex first, and once you know the vertex, it's going to be easier to graph. So we can do this two different ways. We can transform it into standard form, or we can use the shortcut formula. We're going to transform it first, and then we'll do it the other way. We're actually going to do this problem both ways. But we're going to start with our original equation, which is 2x squared plus 8x plus 7. And we're going to complete the square, but we're going to do it in a way that is a little different than how you learned in Algebra 2 when you were solving quadratic equations. When you're solving equations, you're working on both sides of the equal sign. And since you need to preserve equality, the constant that you added in order to complete the square, you would add that to both sides of the equal sign, because whatever you did to one side, you must do to the other. That way you preserve equality. Well, here we're going to preserve equality in a little bit of a different way. Our strategy is a little bit different. We don't want to change the left side at all. We like the nice f of x or y equals. We don't want to change that at all. So we're going to do all of our adjustments on the right side. So rather than adding something to both sides, we're going to take the strategy of if we add something, we have to also subtract it later so that the net effect is 0. Alright, so here's our process. We're going to take our equation, and first thing we're going to do is group the x terms. So I'm just drawing a parenthesis around those x terms. And then whatever the leading coefficient is, including any negative signs, we're going to factor that out. So 2 is the leading coefficient, so I'm going to factor out a 2 out of these x terms. And if I factor 2 out of the first one, I get x squared. And then a very common mistake is forgetting to factor it out of the other one as well. If I factor 2 out of the 8x, I'm going to get a 4x. And then don't forget on the outside, you do still have the plus 7. Now I leave a little room to complete the square. And the algorithm is pretty simple to find the correct constant to add. We simply take our linear coefficient, divide it by 2, and then square the result. So 4 divided by 2 is 2, and then I square it to get a positive 4. So by adding 4 in this spot here, I've changed the value of the function. So as long as I undo that change, then I will have preserved equality. But this is where it can get tricky, and this is the other most common mistake in this problem, is by adding the 4 here, I didn't just change the value by 4. Remember, we have a 2 out in front, which is multiplying everything inside. So by changing this to a 4, I'm really making a change of 2 times 4, which is 8. So to preserve equality, I undo a positive 8 with a negative 8. And now we have preserved equality. So here, cleaning this up a little bit, we get f of x equals 2 times, and now this trinomial, I can now factor it as a perfect square binomial. I know it's a perfect square because I made it a perfect square. That's what completing the square means. And the pattern for factoring a perfect square trinomial is very easy. You simply take the square root of the first term to give you your first term, the square root of the last term to give you your last term, and then the sign in the middle will be the sign in the middle. So that will be x plus 2. And then on the right side, positive 7 and negative 8 combine to be a negative 1. Now we have this in our standard form. And if you think about it in terms of transformations, this is a shift left of 2, down 1. And we're stretching the graph vertically by a factor of 2. So here our vertex, remember our vertex is going to be the value of x that causes this to be 0. That's a much better way to think about it. So the value of x that causes that parenthesis to be 0, that would be negative 2. And our y value is simply whatever that number is, which is negative 1. So plotting that vertex, we go negative 2, negative 1. There's my vertex. Now from there, I get my shape by this number right here. We should remember, hopefully, that the standard shape of the parabola is 1, 1, and 2, 4. Those would be our other reference points. but we're stretching this vertically by a factor of 2. So the 2 on the outside tells us that the y values are going to be doubled and the x values are going to stay the same. So instead of 1, 1, I'm now going to be 1, 2, which gives me that point there. And instead of 2, 4, I'm going to be 2, 8, which gives me, let's see, 1, 2, 3, 4, 5, 6, 7, 8, that point right there. So 1, 1 becomes 1, 2, and 2, 4 becomes 2, 8. We're doubling the y values only. Now also, because of symmetry, I know if I'm 1, 2 on the right, I'm also 1, 2 on the left, because the vertical line going through the vertex will be the axis of symmetry. So likewise, this has a corresponding point over here. That gives us 5 good reference points that we just draw a nice smooth curve through them, and that will give us our graph. So that is our graph, and this is our vertex. Now, we did that by completing the square. We could have also done that by using the shortcut formula. So let's actually take a look at that one. Using the shortcut formula, I would have simply used the fact that x equals negative b over 2a, where b is 8 and a is 2. So substituting in those values, I get negative 8 over 2 times 2, which is negative 8 over 4, which is negative 2. So the x value of the vertex is negative 2, which agrees with what we had here. Now for the y value of the vertex, that's simply f of this negative 2. The value of the function when x is 2, so f of negative 2 means I'm going to take the original equation and replace x with negative 2. Remember to use the parentheses when you do the substitution. And if you do your order of operations correctly, which hopefully you'll be doing by now, you should get negative 1. So negative 2, negative 1 is exactly what we got for the vertex. And then from there, we could have used the original 2, the original leading coefficient, as our vertical stretch. This 2 here is exactly the same as this 2 here. They both have the same effect on the graph. It's going to shift it vertically by a factor of 2. So usually when we graph the parabolas, the easiest way is plot the vertex and then figure out what is the shape, and then that'll give you the other points and draw a smooth curve through them. All right, we're going to look at one more of these, and I want you to try this one yourselves. So this is going to be our question here. Describe the graph, and by that we mean just go ahead and graph it, of negative x squared plus 6x minus 8. And notice how it also wants you to identify the x-intercepts. So we have a little bit of an additional request there. So I want you to go ahead and pause the tape and work the problem. I want you to first use the completing the square in order to rewrite it into standard form, and then plot your vertex and graph your parabola. And then I want you to find the x-intercepts algebraically, which of course would mean we're going to set it equal to 0 and solve for x. So go ahead and pause now and hit play when you are done. Okay, hopefully we're back and you have some sort of an answer. If you got stuck, that's no problem. We're going to work through the problem now. We're going to start out by looking at our original equation, which is negative x squared plus 6x minus 8. And of course, we're going to group the x terms. And then we're going to factor out any leading coefficient, including the negatives. Now, that's all we have here. We just have the negative sign, so we're going to factor out the negative sign, which is really negative 1. And when we factor out the negatives, the negative x squared becomes a positive x squared. The positive 6x becomes a negative 6x. I leave a little room to complete the square, and then don't forget we still have that minus 8 on the outside. Now to complete the square, I'm going to take the linear coefficient, divide it by 2, and square the result. Now we can actually ignore the negative sign here, because when we square it, it's going to become positive anyway. So just thinking of the magnitude here, I can take 6 divided by 2 is 3, and then square that to get 9. So I'm going to add 9 on the inside. Now, to preserve equality, we have to be careful again. The change to the value of the function is not really a positive 9 because there's still that negative sign outside, which means when you distribute that negative, it's really negative times a positive 9 would be negative 9. So you undo a negative 9 with a positive 9. That's where it can be a little tricky. But if you did that right, you should have f of x equals the negative of, and then this trinomial will factor to become a perfect square binomial. And when we do that, we're going to take the square root of x squared to get x, the square root of 9 to get 3, and then the sign in the middle is the sign in the middle. So it's x minus 3 quantity squared. And then combining the like terms, negative 8, positive 9, combine to be a positive 1. So this is our standard form. And from this, you should be able to see that our vertex is going to be the value of x that causes this parenthesis to be 0, which is positive 3, and then whatever this number is. So 3, 1 will be the vertex. If we go to the graph, we go 3, 1, and there's our vertex. Now from that, notice that the graph is going to open downward. So it's going to open downward, and the magnitude on the outside is still 1. The negative sign doesn't mean negative 1, so the shape doesn't actually change. We still have the standard 1, 1, 2, 4 shape. So from the vertex, I'm going to go over 1 and down 1. That's going to give me another point. And of course, don't forget the symmetry gives me another free point. And then also from the vertex, if I go over 2, I'm going to go down 4, which will give me that point. And of course, because of symmetry, we also get that point. So here's 5 good reference points. Just draw a nice smooth curve through them, and you have your graph. Now that's the graphing part of the problem. Now they want us to find the x-intercepts. To find the x-intercepts, we're going to do it algebraically, even though graphically you can actually see that by luck, our reference points did land right on the x-intercepts, or on the x-axis, I mean. So we can see our x-intercepts, but that isn't always going to be the case, so we should see how to do this algebraically as well. And the idea here is that in order to be on the x-intercept, that means the graph has to be on the x-axis, so f of x, which is the height of the graph, has to be 0. So if I take my original equation, which is the negative x squared plus 6x minus 8, I have to set that equal to 0 and then solve for x to get the x values of the x-intercepts. Now, I notice a common error here is a lot of people factor this by making one parenthesis x and then the other parenthesis negative x. And you can do that. That can be done, but it gets a little confusing when you're factoring with a negative leading coefficient. So something I like to do is to work smart rather than hard, and I'm just going to multiply through by a negative 1, and that way I get a positive x squared minus 6x plus 8 equals, and negative 1 times 0 is still just 0. So now I have a quadratic with a positive leading coefficient. Much easier to factor. So since I have a trinomial where a does equal 1, I can go right to my double bubble, which is my 2 parentheses. To get x squared, that's simply going to be x times x. And then for the other 2 numbers, I ask myself the question, what are factors of positive 8 that add up to negative 6? And that would be a negative 2 and a negative 4. The product is positive 8, and the sum is negative 6. So once I have it in factored form, I now ask myself the question, what is the value of x that causes each factor to be 0? Because those are going to be the x values of our x-intercepts. So the value of x that causes that to be 0 would be 2. The value of x that causes that to be 0 would be 4. And since x-intercepts are actually points, these are going to be ordered pairs. When x is 2, we know that y must be 0 because we're talking about x-intercepts. All x-intercepts have y values of 0. So these two x values will correspond to these 2 points, 2, 0 and 4, 0, which we can verify with our graph. Okay, let's look at an applied problem. We're going to look at a word problem. And here we have finding the maximum height of a baseball. Of course, a baseball's hit 3 feet above the ground, velocity is 100 feet per second, angle is 45 degrees with respect to the ground. This function gives us the path of the baseball, where f of x is the height in feet, and x is the horizontal distance from home plate in feet. And the question is, what is the maximum height reached by the baseball? Okay, we've actually seen a problem similar to this in the last section, or the last chapter. And to do that, we use the calculator. But now we actually have the tools to be able to do this algebraically. So we're going to do this one algebraically. The idea here is we're going to take our original function, which is f of x equals that. And we want to first notice that this is a quadratic equation, so its graph is going to be a parabola. Furthermore, the negative leading coefficient means this parabola is going to open downwards. So the path of that ball will be a parabola that opens downwards, which we should expect from physics because projectile motion is modeled using quadratic equations. So when we go ahead and think of that parabola, that maximum point, that maximum height, is going to occur at the vertex. So I simply want to know what is the height at the vertex, maximum height. Since height is f of x, which is the same as y, I want to know what is the y value of the vertex. Now, unfortunately, I don't have an equation for the y value of the vertex, but I do have an equation for the x value of the vertex. That's simply x equals negative b over 2a. So substituting in the values here, notice how b is 1 and a is that decimal. We're going to have negative b over 2a would be negative 1 over 2 times negative 0.0032. Now I do want to point something out putting that into the calculator. Let's take a look at, if I go to the calculator and I go to my home screen, if I simply enter in that equation just the way it is, depending on your calculator, which we're using the TI-84 here, you might get the wrong answer. So again, that was negative 1 divided by 2, open parenthesis, 0.003, oh, I'm sorry, it was actually negative. Back that up to negative 0.0032, close parenthesis. So if I enter it in just the way I see it here, I'm actually going to get the wrong answer. That is not the correct answer. And the reason is, this calculator knows the order of operations. And if you enter it in like that, it takes that as division and that as multiplication. Since multiplication and division are the same order of operation, the rule is to do them from left to right. However, when we look at it here, this is really a division bar. This is different than the division sign. The division bar is also a grouping symbol. So the division bar means the entire numerator divided by the entire denominator. So therefore, the correct way to enter this into the calculator would have been negative 1 divided by, and then I'm going to open a parenthesis for the entire denominator. And inside I'm going to say 2 times negative 0.0032, close parenthesis, and now it's the numerator divided by the entire denominator. And now when I hit enter, I do get the correct answer, which is 156.25. So if you enter it into the calculator correctly, you get 156.25 feet. And just for our notes, we'll put here that be careful when entering, because this one was the wrong answer, this one was the right answer. So once I do know that x is 156.25 feet, then to find the y value associated with that, I would simply substitute that into the original equation. In other words, I want to know what is f of 156.25 feet. So here we substitute everywhere we have x, we replace it with 156.25. And as long as you follow your order of operations, do your exponents first, then your multiplication, then your addition, then you should get your y value being 81.125 feet, which is the maximum height reached by the baseball. And now, I did add a little bit more to the question. I also want to know, where will the ball land? So when the ball lands, the idea here is that when the ball does actually land, think about our parabola again. When the ball lands, it's going to hit the ground, which means the height will be 0 when the ball hits the ground. So f of x will be 0. So I can do this algebraically by setting this equation equal to 0 and then solving for x. But I don't feel like doing that because that would be a little tougher to do by hand. So we're actually going to do that one on the calculator. But we could do it, of course, by using either completing the square or the quadratic formula. The quadratic formula would probably be a better approach here. But I don't want to get into all those calculations. We're going to see how to do it on the calculator. So the idea on the calculator, graphically, when f of x is 0, then we're talking about the x-intercepts. So our strategy here is to find the x-intercept. And let's take a look at that on the actual calculator. Okay, first of all, and I did skip one thing. Whenever you turn your calculator on, the first thing you should always do is check your mode, especially when you're borrowing one of the calculators in class. So if you check along the left side here, that for our purposes now, we just want everything on the left to be selected, because you never know who used the calculator before you, so it's always a good idea to check your mode first. And once we see our mode is correct, now we're going to go to y equals, and we're going to enter in this equation exactly the way it is. We're going to use, remember, f of x is y, so it's y equals this equation, which is going to be negative 0.0032 x squared plus x plus 3. Let me double check that. Yes, that is correct. All right, once we have our equation in there, we're going to get a graph by selecting our domain and letting the calculator figure out the y values. So we have actually seen a problem with these numbers before. We had a problem in the last chapter with the exact same equation, and it asked us to whether or not that ball would clear a fence that was, I believe, 10 feet high, 300 feet down from home plate. So if you remember the numbers there, then you know it should land a little further than 300 feet. But even if you don't know about that, you can use reasonable values. If you think about National League baseball parks, you know, their home run walls range anywhere from about 310 to about 420 or so. So I'm just going to pick a number somewhere in the middle, like 350. And then if we need to adjust it, we'll adjust it. So in other words, on my window, if I go to window, my x-min is going to be 0, which it will be at home plate. And I want to see what happens from there to, let's say, 350 feet away. And if I need more room, I come back and I change my window. So once you select the x values, I don't even care what the y values are, because I'm going to let the calculator calculate them. So in order to do that, I'm going to go to zoom, and then the very last option, which you can arrow down to zoom fit, or hit the up arrow and it brings you to the bottom of the list. Or if you know it's 0, you can hit zoom 0. But zoom fit is the function that will take the x values that you chose, and it will determine the y values so that all of your data points are in the graph or on the screen. So for zoom fit, I'm going to go to zoom 0, which gives me that parabola. So again, it's a nice and easy way to get a very good window for your data. So we see here it lands somewhere around there. We know it's 0 to 350, so that's a little less than 350. And the question is exactly what is that point? Now we could hit trace and arrow over and get a good estimate of that point, but if we want to know exactly what that point is, within so many decimals that the calculator can handle, then we want it to calculate that x-intercept. But before we get that, we're going to go back and look at that maximum height again. We're going to make sure that we can still do that on the calculator. So to find the maximum height, I want to see what this point is right there. So what I'm going to do is I'm going to go to Second Trace, which is the Calculate menu. And here I want to find the maximum, so I'm going to choose option number 4. And so it's going to ask me for left bound, right bound, and a guess. So left and right bound, I want to set an interval that will capture that maximum. Now this is pretty easy with parabolas because the whole thing has only one maximum there. It only has one extreme value. So I can really use the whole window as my left and right bounds if I want. It makes it nice and easy. So left bound, I'm going to choose 0. Enter. Right bound, I'm going to choose 350. Enter. And I know I can only capture one of them. Now the guess doesn't matter. Just hit enter. And there's your maximum value. Notice how we still get 81.125 feet, which is exactly what we got here. Now, next we want to find what is that intercept right there. So in other words, I want to know where does the value of this function equal 0. That's how we find the x-intercepts on the calculator. So again, I'm going to go into Second Trace, which is the Calculate menu. And I want the 0 of the function. Don't be confused with intersect. Intersect is where two curves overlap each other. I don't want the intersect, I want the intercept, which is where the value of the function is 0. So I actually want the second choice here. So I'm going to choose option number 2. And again, it's going to ask for left and right bound to capture that. Now, here I could have more than one intercept. Notice how I only had one maximum value. So I could use the whole window. But here, to be safe, I'm just going to look on the right side of the window. Now technically, because the equation has the +3 at the end, I know that if the x's are 0, that this point is really 0, 3, so it doesn't actually go through the origin. But just in case, I'm going to build the habit of looking only on the right side and tightening up my boundaries a little bit so I make sure I capture only that intercept. Alright, so left bound, I'm going to choose somewhere in the middle, let's say 200. That'll be my left bound. Hit enter. And then right bound, I'm going to use the edge of the screen, which is 350. Enter. And again, the guess doesn't matter. So we get the 0 is 315.47 is that x value. So putting that over here to answer this question, we see that our x value of the x-intercept is 315.47 feet is where that ball is going to hit the ground. And that would actually conclude that problem, but I do want to do a quick recap because I'll have these screen captures in the notes. So a quick little recap of that process is first we take our equation and put it into our y equals. This is after we determined we're in the correct mode. And then we want to go to our window and determine the values of x that are reasonable for our problem. And then let it determine the value of y's by going to zoom fit. So if you put in your correct x values, go zoom fit, you should get a graph that looks like that. And to find the maximum, we're going to go to Second Trace, which is the Calculate menu. We're going to choose option number 4, which is maximum. And as long as you choose the left and right bounds that are going to capture your vertex, then you'll find your maximum is 156.24, 81.125. And the interpretations there is that 156.25 feet downfield, the ball will be 81.125 feet in the air. So that will be the maximum height because f of x or y was the height. And then where will the ball land? We can simply, from this graph, we can go to Second Trace to be the Calculate menu. This time we're going to choose option number 2 because we want to know where does the value of the function equal 0. And choosing the proper left and right bounds, you're going to find that that happens at 315.47 feet. All right, that wraps up this lecture on quadratic functions, and we're done.